Okay, so today I was going to start chapter 6, so I should get through the first section of chapter 6, no problem. And it's so kind of in keeping with the stuff we did in chapter 4. A lot of this stuff is going to be, of course, stuff that you're familiar with and you've seen in some form. We're just going to be obviously a lot more rigorous about it this time around. So, goal really in this chapter, so I should say goals for chapter 6. It's the following. So, define the notion of an integrable function. And for such functions, define the integral, this thing. Okay. And I'll mention where some of this stuff leads immediately. So there's some slight generalizations I'll be able to talk about that will make some sense. There's some other generalizations I will still talk about that won't quite make a lot of sense, but I'll only mention them briefly just so that you see kind of where this is headed. Goal number 2 is prove that continuous functions are integrable. Okay. Okay. So it turns out the class of functions that is integrable in some meaningful way is larger than the class of continuous functions, but continuous functions are contained in them, and that's what we care about for the most part. So to that end, I'm going to show some examples of functions that are not integrable, and of course, if this is going to be a goal that we actually attain, what that means is for anything that is not integrable, it would necessarily have to be discontinuous, right? Okay. And then goal 3 is to prove FTC 1 and 2. Okay, if you don't remember FTC, Fundamental Theorem of Calculus 1 and 2. So these are both directions of the Fundamental Theorem of Calculus. So it is establishing that this integral is the antiderivative, right? So the integral is the antiderivative, i.e. integrating is the inverse operation to differentiating. Of course, you all know this well, but we want to show both of these things. So FTC 1 and 2. So I've abbreviated it here by calling it FTC 1 and 2. If you want to see the full statements, we're gonna get to that before the end of this chapter. But anyway, so you might recall a starting point for defining this definite integral is to define it as the area underneath the graph of f on the closed interval a to b. Okay. In fact, if you remember how this was done intuitively for you, going all the way back to Calc 1, this is exactly what was mentioned, or this is exactly how it was handled. Now, there's other interpretations of the integral. So you might recall from physics, you can think about integral as with a suitable interpretation of your function. You can think about integral as telling you something about total distance traveled, or you could think of it as an averaging thing. The point is, like, there's a ton of different interpretations we could think of the integral. This one is kind of the most intuitive, and one of the nicer things, especially for actually showing for actually proving facts about it. So that's what we're going to use. All right, so this is how we're going to define this integral. So in order to do this, you might recall that the starting point was to consider graph some generic function on closed interval a to b. What was the starting point for defining the integral as area under graph of f? So you might remember from Calc 1 that the starting point was you considered a partition of this closed interval AB. So I have some partition. I'll write that out precisely in a bit, but a partition is basically a choice of some subintervals, right? And of course, a given partition here, I'll throw in a couple of these. Given partition need not be equidistant, so these points need not be equally spaced, of course, but for the most convenient partitions, that would be the case. But anyway, there's no reason that our partition is going to be super convenient or anything. What was the next step? So the next step was then to define some rectangles that are going to count the area, or rather approximate the area under this piece by piece. All right, so maybe one of the easiest things that was discussed was like a Riemann Left Sum, right? It was called back in Calc 1. So a Riemann Left Sum, basically whenever you're picking these rectangles, you have to pick what is going to determine the height. Right? So in a left sum, what you said determined the height was a choice of the left endpoint in each of these subintervals. And so you chose the left endpoint of each subinterval that resulted from this partition, and you said, all right, the height of my rectangle is going to be the functional value above that endpoint. All right, so for instance, this would be the Riemann left sum. So here's my Riemann left sum, where I've used the left endpoint of each of these subintervals to determine the height of my rectangle. And then I would say that if I were to sum the area of each of these rectangles, so I have rectangle 1 and rectangle 2 and rectangle 3 and so on. If I were to sum the area of those rectangles, which is easy to compute, I would get an approximation of this area underneath f. And then in order to talk about this definite integral, I would take the limit of this process in some way, right? So I would let the number of subintervals go to infinity. Now, there's a couple of problems with this approach. So you might recall that one thing you notice is that for this particular choice of partition, there's some underestimation here, but then there's some overestimation here, right? So I'm just going to shade the bits that are over or under. Okay, now for a given partition, this is actually this might be good, right? Because you have some underestimation, then you have some overestimation that can kind of compensate for that. So for a given partition, maybe this actually gives you a more accurate result if you were to use some other method. So you might recall that there was the Riemann Right Sum, which is you chose all of the right endpoints instead, right? Here's something, right? One of the reasons why this was done in Calc 1, and this wasn't even the only thing you did in Calc 1. We talked about this stuff, but using a left or right sum was nice for actually having to compute some of this stuff, right? So maybe back in your early calculus days, you actually had to compute some of these sums. You actually had to add some of these together. So for those purposes, using the left or right sum, or even a midpoint sum, you might recall, was another thing that you could do. That was actually easy to do by hand. But actually proving facts using a left or right sum is kind of tricky because you can never tell if it is actually overestimating in general or underestimating. In fact, it depends on the shape of the function. Right? So for instance, if this function were entirely increasing, you might be able to see that if I have a function, wherever this function is increasing, a left sum is going to underestimate it. Right? On the other hand, wherever a function is decreasing, a left sum is going to overestimate it. Right? So the shape of the function would determine the behavior of that sum, and for various reasons, that's kind of annoying. So what we are going to want to use instead of thinking of left and right sums are upper and lower sums, okay, which we're going to call upper and lower Darboux sums. Okay, and so the idea with an upper and lower sum is that an upper sum always overestimates and a lower sum always underestimates. Okay, so how does this work? Again, I consider a partition. Say it looks like that. And on each subinterval, I look for the largest, for the upper sum, I look for the largest value of the function on that subinterval. And for the lower sum, I look for the smallest. So let's say that I'm doing the lower sum here. Okay. Now, this function is continuous. And so on each of these subintervals, of course, it has both a min and a max, right? This is a result of the extreme value theorem. So I'm always guaranteed to be able to find this. So then, for instance, on this subinterval, what is the smallest value? Well, it's here. So that's the height of my rectangle. On this subinterval, what is the smallest value? It, just eyeballing it, it kind of looks like it occurs here. Okay, on this subinterval, what's the smallest value? Here. Okay, on this subinterval, what's the smallest value? Well, it's still here. On this subinterval, what's the smallest value? It occurs on the right endpoint. Now, sorry. Why did I draw that? That's bad. That's bad. Ignore that. Okay. All right. So that's what my picture looks like. So notice that this thing underestimates at every step, right? The way that this is chosen, by definition, the height of this rectangle is always going to be below this curve. And so this is always going to underestimate. Similarly, if I had used an upper sum instead, it would always overestimate. Now, there's a couple of things. So one, describing how that works, of course, is just as easy as describing a left or right sum. But imagine that you were trying to do this by hand. One thing is, in this case, it wasn't so bad because it was easy. Once we had the graph of the function in front of us, it was easy to pick which point the upper or which point the lower thing happened for this function. But imagine, for instance, I had done the upper sum on this function. On this subinterval, the maximum occurs here, which is some point in between my endpoints. So for an upper or lower sum, it could happen that there's a point that is not one of the partition points, we'll call them. It's not one of the partition points, but it is the point whose functional value determines the height of the rectangle. And how would you actually figure out such a point if you were trying to do this by hand? You would have to use, going back to Calc 1, you'd have to use like the first derivative test, right? You'd have to use some derivative test to actually check critical points and find where maxes or mins happen. So computationally, this would be really annoying. But lucky for us, we're not going to be dealing with that too much. We're not going to be computing with these things too often. And it turns out that the mathematical properties of the lower or upper sums are a lot nicer. Right? This is a lot more chaotic. This is very nice because every lower sum always underestimates. And on the other hand, every upper sum always overestimates. So that's nice. Okay, so that's the intuition down. Okay, so then some definitions. So let A and B be real numbers with A less than B. If n is a natural number and A we will call x naught, and this is strictly less than some x sub 1, which is strictly less than some x sub 2, and so on, all the way out to x sub n minus 1, strictly less than x sub n, which we are calling b. If we have this setup, then P, which is really just the set of partition points here, so it's the set of these x sub i's. This is called a partition of that closed interval. So you might remember this from your Calc 1 days. So this is called a partition of closed interval AB. All right, so for each index I, x sub I is called a partition point of P, and if we have index less than or equal or greater than or equal to 1, then the interval x sub I minus 1, x sub I is called a partition interval or subinterval. So I'll use subinterval interchangeably with that. Now you might note that the simplest partition possible is a partition with two partition points A and B. So example, what if my partition is just AB, right? So A is x naught and B is x sub 1. Since A is less than B, x sub naught is less than x sub 1, and so it's partitioning my closed interval into a single piece, right? Okay, so the idea here is, of course, partitioning this into a bunch of disjoint pieces. So I'm going to make some assumptions. So suppose that the function f from closed interval into the reals is bounded. Note, before I go any further, this is going to be automatically true for continuous functions. Why? Well, if I have a continuous function on a closed interval, then by the extreme value theorem, it is bounded above by its max and bounded below by its min, right? Both of which are attained on this closed interval somewhere. So, so this is automatically true for continuous functions defined in this way. So suppose that the function f is bounded and p is a partition of its domain. Okay. We're going to define some things, okay, that are very important. They're not just throwaway quantities. These are going to be used throughout this section in these proofs. So define the following. So for each index I, m sub I is defined to be the infimum of the set of functional values such that x is in the subinterval x sub I minus 1, x sub I. Guess to be correct here, we define these for indices greater than or equal to 1. So define for each index I greater than or equal to 1. And big M sub I is exactly as you think. It's the sup of the same set. Okay, so let's stop for a second. What is little m sub I? So this is the infimum of the set of all functional values ranging over this particular subinterval of this partition. Okay, the ith subinterval, if you like. Similarly, this big M is the sup over that same set. Okay, so you probably see where I'm going with this. Then define the following. So we have L of Fp is defined to be the sum from I equals 1 to n of m sub I times x sub I minus x sub I minus 1. Oop. Okay. And U Fp is defined to be the sum from I equals 1 to n. It's a really bad looking sigma of big M sub I times x sub I minus x sub I minus 1. Okay. All right, stopping again for a second. What is it that I'm doing here? So this is my lower Darboux sum. This is my upper Darboux sum. So these are lower and upper Darboux sums. I don't speak French. I don't know if Darboux or Darboux is closer. I'm going to say Darboux. I'm just guessing. I can't really remember. So, anyway, these are upper and lower Darboux sums. Okay. So, what is it that I'm doing here? So one, what is this quantity? This x sub I minus x sub I minus 1. So at each step, at each subinterval, what is this computing? It's just computing the width of the base of these rectangles, right? This is just the distance from, the x sub I partition point to x sub I minus 1, the one right before it. So that is the distance. That's the length, or rather the width of the bottom of these rectangles. And this is going to be the height at each step. So this is saying that at each term in this sum is an area of one of those rectangles, right? So this one is the sum of all of those areas where the height, so the base is predetermined. The base is what the base is going to be regardless. Then the height is determined by these little m sub i's. That's why it's a lower sum. And so the height is determined by these little m sub i's for the lower sum, and it's determined by the big M sub i's for the upper sum. Rather than waste time drawing a picture, I'm going to just put this picture here. So basically you can see directly from the textbook. So this is a description of what, here, let me get that closer to the camera. Will it focus? Hold on, there's a focus button. Maybe it will focus. Ah, there we go. Okay, so this is a depiction of little m sub I and big M sub I. I don't expect you have much of an issue understanding what those do. So this is a nice picture. And then showing the difference between L and U, this is what's going on. Again, note how the lower sum always underestimates and the upper sum always overestimates. Okay. All right. Now, a bit about notation. So for the notation of these, notice we say this is L of FP. Why do we use F and P here? So this is to show that these things obviously depend on F. Well, that's clear. But obviously they also depend on the partition, right? So even with the same function F, the partition very much determines these values, right? Choosing a different partition chooses, or is going to, in general, result in a different value for these things. Okay. Let's refocus this. Oh, there we go. Okay. All right. So, obviously, little m sub I is less than or equal to big M sub I for all I. So that's clear. And thus, for any partition P, it's true that the lower Darboux sum is less than or equal to the upper Darboux sum. Okay. Now, intuitively, it should be true that once we have a working definition for integral, it should be true that if it is anything like the notion of integral that we understand, it should be true that, I'm going to put this in quotes, it should be true that this definite integral is bigger than or equal to the lower Darboux sum and less than or equal to the upper Darboux sum. This is just our statement that from those pictures we just looked at, it was clear that the lower sum is always underestimating and the upper sum is always overestimating. Okay. All right. So, one more thing that I want to get into before I start proving some facts about these things. So I have a couple of tricks up my sleeve, and there's something that is used very frequently in several of these proofs. So there is, we'll say, one weird trick. We can think of b minus a, that is the length of the entire interval, as being computed from this following sum for any partition. Right? So this is true for any partition P made up of these partition points. So think about why this is. This sum telescopes in a really nice way, right? So just evaluating like a few terms here, right? So this would be oh, this needs to go from does this work? Oh no, this works out fine. So yeah, so the first term would be x sub 1 minus x naught, and then the second term would be x sub 2 minus x sub 1. So x sub 1 cancels the minus x sub 1, and I'm left with x sub 2 minus x naught. But x naught is a, right? And this telescopes in an obvious way. All the middle terms cancel out, and so the only term you get is x sub n, which is b, minus x sub naught, which is a. Okay, so thinking of b minus a as this thing is useful. Why is it useful? Well, you see this showing up in the definitions of the lower and upper Darboux sums. So knowing that, then basically this is going to tell you that there is like a natural thing, there's a natural algebraic trick that you can apply to get an upper or lower Darboux sum showing up out of anything that involves this. Okay, so in fact we're going to use this trick immediately in the following lemma. So suppose that the function f defined on the closed interval ab is bounded. So suppose it is bounded and there exist numbers m and little m and big M such that, I mean, this word and is a little confusing here because I'm implying that's different than this thing just being bounded. This thing being bounded exactly means what I'm writing, so little bit bad with my English there. Okay, so suppose that you have a bounded function and little m and big M are the upper and lower bounds. Okay, then if P is a partition of AB, M times B minus A is less than or equal to the lower Darboux sum of F on the partition P, and the upper Darboux sum is less than or equal to big M times B minus A. Okay. So what this is saying is that the lower Darboux sum is bounded below by the lower bound of f times the length of the interval, and the upper Darboux sum is bounded above by the upper bound of f times the length of the interval. Okay, so the proof of this is actually fairly straightforward once we know this trick here. Okay, let's P be a partition of AB in the usual way. So P looks like this. Okay, where x naught is A and x sub n is B. Okay. M sub I defined as usual. When I say as usual, I mean in the same as it's defined in the definition for the Darboux sums. So then it is clear that m is less than or equal to, little m is less than or equal to little m sub I for all I. Well, why is that true? So little m sub I is the infimum of the set of functional values for f on some given, some ith subinterval, right? But little m is this lower bound of f, right? So because this is true, it is certainly going to be a lower bound. This little m is a lower bound for f on the entire interval. So then it is certainly going to be a lower bound of f on each subinterval. And since little m sub I is the infimum of those functional values on each of those subintervals, then it's still some functional value. And since little m is itself a lower bound for all functional values, it's certainly less than or equal to m sub I for all I. Okay. All right. So then what is true? Well, I want to show that this is less than or equal to this sum. You might already have seen what's going on here just from this trick. So what do I want to do here? So m times b minus a. Well, using this trick, this is m times the sum from I equals 1 to n of x sub I minus x sub I minus 1. This is a finite sum. I mean, even if it wasn't, it wouldn't be a problem. But this is a finite sum, so there's no funny business going on here. I can just move m inside this sum. So this is the sum from I equals 1 to n of m times x sub I minus x sub I minus 1. Okay. But again, by this fact, this is less than or equal to the sum from I equals 1 to n of m sub I, x sub I minus x sub I minus 1. But that's exactly the lower Darboux sum of f relative to that partition P. Okay, and it's a similar argument for the other direction, so similar argument for the other inequality. Okay. All right, so that's good. So what this is saying is that these lower and upper Darboux sums are both. So the lower sum is bounded below and the upper sum is bounded above. And this means that both of these things are bounded. Now, one, you can actually see the particular bound, right? So we didn't say anything about like little m and big M being like the sharpest possible bounds. We didn't say anything about little m and big M being like literally the min and the max of f, even though that's what you're thinking. But then, thinking about it concretely, what is this lower bound, right? This lower bound is some like really dumb small rectangle, right? And this upper bound is some really dumb huge rectangle, or the area rather, I should say, of some really small rectangle versus really big rectangle. Whereas this rectangle is the width of it is, the bottom width is the length of the entire interval, and its height is again, because I didn't say that this was the max, but say that this is the max of f. This height then is the largest possible value of f. Same thing here. This tiny rectangle is, its width is the entire length of the subinterval, and its height is the smallest possible value of f. Okay, so it makes sense when you think about it in those terms. So I have to define something else before I can state the next theorem. I have to define the notion of a refinement of a partition. Okay, so definition. This is refinement of a partition. So what is a refinement? Let P be a partition. Be a partition of AB, then P star is called a refinement of P if each partition point of P is also a partition point of P star. Okay. All right. So let's think about this intuitively. What does this tell us? Well, so if you have a refinement of a partition, I mean, the easiest thing to think of is, say I have a partition of AB. Maybe it looks something like this. So, of course, I have the endpoints included, but there's my partition. So, partitions AB like this. This is P. Okay. Then what would some refinement of that look like? Let me draw a copy of this thing. So, I have the endpoints included. I have a point like right here. I have a point here and here. Maybe that wasn't totally good. But so these points match up. So maybe I'll toss in an extra point here and here so that I get 2 points added. So one here and one here. Right, so every other point that was in P is in this new P star partition, but P star has additional points as well. So why is it called a refinement? So think back to what this would mean in the picture, right? Tossing in more points, so taking partition, tossing in some more points does what? Well, and why is it considered a refinement? This would amount to cutting up, right, that area into slivers of smaller rectangles. This just means more subintervals in those Darboux sums. And you remember that intuitively, if we're going to think about approximating that area, and we want to think about approximating it as well as possible, more subintervals means that we are more accurate, right, intuitively. So that we get closer and closer. The more points that get thrown into some partition, we get closer and closer to the actual value that we're trying to compute. And so that's why it's called a refinement. So what does this mean? So note in particular that for all indices I greater than or equal to 1, the partition points of P star that belong to the partition interval x sub I minus 1 to x sub I. These are partition points of P. Define a partition P sub I of the interval x sub I minus 1 to x sub I. Now remember, sometimes the only partition points in the refinement that are actually going to be in this subinterval are going to be the endpoints. And of course that's allowed just to make sure that this always makes sense and we don't have, because this statement isn't going to make sense otherwise. So anyway, so basically another way of thinking about it is the refinement allows you to partition each of the subintervals. Sometimes that partition is going to be the stupid partition where you're not actually partitioning it. Remember, the dumbest possible partition is just the endpoints, right? So it's just the partition that does nothing. It just considers the interval as a single subinterval. But in general, it's going to be partitioning. So for instance, we added in a point here in between these two and P. So in P star, I get a partition of this. So this was a single subinterval in my original partition. This gets partitioned, right, into these two pieces in P star. Okay, so that's another way of looking at it. And then furthermore, note also that the sum from I equals 1 to n of the lower Darboux sums for these P sub I partitions that are partitions of the partition P. If you sum up all of those, this actually is the Darboux sum of, or relative to, the refinement P star. And similarly, the same sum for the upper Darboux sums is the upper Darboux sum relative to, for F, relative to this refinement P star. Okay. All right, so a couple facts that I want to state. So I have another lemma I want to prove. This is called the refinement lemma. Okay, so suppose that the function f defined on the closed interval AB is bounded. Again, I want to stress that, notice this would be automatically satisfied for continuous functions by the extreme value theorem. And that P is a partition of AB. And, or maybe I should state it like this. So if P star is a refinement of P, then the Darboux sum of F relative to the partition P is less than or equal to the Darboux sum of F relative to the refinement P star. And the upper Darboux sum of F relative to the partition P star is less than or equal to the upper Darboux sum of F relative to the partition P. Now, before I get into a proof of this, I want to think for a second. So what is this saying intuitively? So intuitively, what this says is if we know that the lower Darboux sum is always an underestimate and the upper Darboux sum is always an overestimate, well, in that case, when I look at a refinement of a given partition, then the lower Darboux sum associated to that refinement is, in general, a little bit bigger than the lower Darboux sum associated to the original partition I started with. And so as I continue refining my partition, what is it that's happening? This lower Darboux sum is getting bigger and bigger and bigger. That is good because that's telling us that as we consider refinements and refinements of refinements, our lower Darboux sum is getting closer to the real value, right? Since we know that it's an underestimate, it increasing, intuitively it's telling us it's getting closer to the actual value. Similarly, for the upper Darboux sum, it's getting a little smaller, and since we know that the upper Darboux sum always overestimates, this is good. It means it's getting closer to the actual value. Okay, so intuitively that's what's going on. All right, so this is just a little bit of bookkeeping, actually. We're just going to apply this lemma that we proved just a second ago. So what's the proof of this? So let P be partition, usual notation. So there's P for an index I greater than or equal to 1. Let M sub I be defined as usual. Okay. Let P sub I be defined in this way that I just let me grab that sheet of paper. So I define P sub I to be this further partition of the subintervals that I get from the refinement. Okay, so let P sub I be the partition of x sub I minus 1, x sub I, induced by P star. So this isn't defined in the textbook, but what is meant, you use a big word like induced, is we will say that this partition P sub I that results from considering a refinement as a partition of the subintervals in the original partition, we will say that P sub I in this way is induced from P star or is induced by P star. Okay, so that's the terminology we'll use. Okay, so this follows, like I said, on that previous sheet. This is where my P sub I comes from. Okay. Then by the previous lemma, what does this mean? So by the previous lemma applied to my function f restricted to this particular subinterval. So what does this mean? What I get is that m sub I times x sub I minus x sub I minus 1 is less than or equal to L f of P sub I. And this is true for all I between 1 and n. Okay. But I can just slap sum signs here. Right? So if I slap sum signs here, I going from 1 to n, I get this on the left. Right? So on the left I get this sum, and on the right I get the following sum. And of course, this inequality is respected because I'm just summing these things. But what is this? I mean, this is the definition of the lower sum. This is L, F, P. So this is the lower Darboux sum. Oh, sorry. This is the lower Darboux sum of F relative to the partition P. And so that is less than or equal to, what is this? Well, without thinking about how these partitions work, you might be a little bit stuck here. But remember, I already smoothed this out for you by saying, note that if you sum the Darboux sums over these partitions that are induced from the refinement, you just get this thing. You get the lower Darboux sum of F relative to the refinement itself. Aha. And we're done. Similar argument for the other direction. In fact, if you're a little bit confused by this, it's a good, for both of these lemmas, it's good practice to go back and do the other direction. So similar argument for other inequality. Okay. All right. So I think here's a good stopping point. We have a couple of more lemmas that and a particular example that I want to make sure that I go over before a big theorem that I prove next time. So I think here's a good stopping point. I'll stop here. We should, by the end of the week, we should have a good chunk of chapter 6 under our belts. And again, there's some lectures that I'm going to record and upload outside of these live streaming times. I will also post the first homework you've had since after the break. It won't be due till the end of the semester, as I said before, but obviously it's in your best interest to do it to do it before then, as we're actually going over this stuff. So that homework will cover from like the very end of chapter 3, since we didn't get homework from that stuff, like one section from chapter 3. It will cover the last section of chapter 3 that we did and all of chapter 4. So that the next homework that I assign after that, which I won't until we're I won't do it until maybe the beginning of next week. I'll assign some stuff from chapter 6. So anyway, that's the plan. So when will problem set be released? I'll post it sometime later tonight. I have to update. I'll add a bunch of stuff to Elms under the syllabus. Also, for future reference, I'm just going to make the links public. There's not that many of you anyway. I'm just going to make the YouTube links public, so you don't have to wait on an Elms announcement when I'm going to go live. I'll just go live at this time every Tuesday and Thursday, so that I don't always have to post the link. If I'm not going to do a live stream that day, I'll record a lecture and post it and let you know, so that you're not like sitting waiting on me to go live. So I would let you know beforehand if I wasn't going to do a live stream on some day. So anyway, and then I'll announce some live stream, not lectures, but basically problem sessions. Once I've put out the problem set and you've worked on them a little bit, if you have questions, you can ask, and I can go over some of them. Okay, so that's the plan for now. But anyway, I will see you all on Thursday. Like I said, if I end up not live streaming on Thursday, I will just record it sometime before then or sometime soon after and post it and let you know about that. But I'm going to clean up the YouTube channel as well, so that it's more organized. I know right now it's kind of a mess with all my other classes on the same thing, but I'm going to split up all the video categories and so that it's a lot nicer. Yeah, actually, I just was able to. Yeah, I will add those too. I was able to sneak onto campus and get them. So. I was able to do that. I just haven't added them yet. But yeah, I thankfully I was able to get everything off campus, so I won't have to go back because it seems kind of impossible to get access to stuff now anyway. So anyway, but yeah, I was able to get them, so I'll add them later. Okay. Anyway, so I'll let you know about all that stuff, and I will see you all on Thursday.